We learned in physics 20 that diffraction is the spreading out of a wave. We also learned it last week, at least we introduced it last week, this whole concept of diffraction and interference, diffraction being the spreading out of a wave. We saw this example last week when this wave coming from the open ocean is coming to this little opening in the rocks. The wave ends up going through at least that small narrow section of the opening, and then it spreads out like this. Refraction is the bending of a wave, and that happens when a wave enters a new medium, changes speed, and therefore changes direction. Okay, but diffraction, we don't have the wave changing direction. We've just got it spreading out, still going in a straight line, but spreading out as a result of that opening or going around that barrier. Now, when we have two openings, we know we're going to get diffraction taking place, or the spreading out of a wave taking place in two places. When those two waves that are spreading out encounter each other, we get interference. When two crests encounter each other, we get constructive interference. We get a bigger crest. When two troughs hit each other, we get constructive interference. It's a bigger trough. When a crest meets a trough, we get destructive interference. We get complete cancellation of the wave. This diagram that you see right here is like having two openings. What it really is two tennis balls being bounced in the water, producing these waves. It's the exact same pattern that you'd see if you had two openings, though. And you can see that we have two diffraction patterns, and they're interfering to produce two of these. These two diffraction patterns are interfering to produce this interference pattern. And in this interference pattern, you see that you get this area right here of constructive interference. Big waves, big crests, and big troughs. And you get the same thing right here, constructive interference. And right here, constructive. And right here, and right here, and right here, constructive interference. But in between those lines of constructive interference, we get complete cancellation of the wave. We get destructive interference. Let's switch that color a bit. Destructive interference. Here, there's no wave there. Destructive interference. Destructive, destructive, and destructive. You get these alternating lines of big waves and no waves, of constructive interference and of destructive interference. Hey, and if this is a water wave, we can see it just fine by standing above it and looking at it. Hey, just like this photograph right here, you can clearly see in this photograph, or at least you could before I do these highlighted lines on it, these waves that are bigger and these areas of no waves. But if this is light, we can't just see it, because light has to reflect off of something to see. So what we do is put a screen on the other side. We put a screen down there. We end up getting this middle area, this spot in the middle of constructive interference. That would be a bright spot on the screen. And then right beside it, we get an area of destructive interference where it's a dark spot. In other words, the absence of light. And then beside that, another bright spot, and so on and so on. So we end up getting this pattern on the screen that looks more like this. Bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, and so on. You guys remember that from last Thursday or whatever day it was that we did it? Can you ring a bell? Makes sense? When we represent those bright spots and dark spots by a graph, then the graph would look something like this. Something like this. Should be curved at the top more. But this is intensity versus position. The intensity of the light right here is high. The intensity of the light right here is 0. It's a dark spot. There is no light there. And then it's higher again, but not as high as it was the first time. And then it's 0, and then it's higher again, and so on and so on and so on. So this is our actual pattern that we'd physically see on the screen. This is a graph of the pattern of intensity versus the position. Now, This is where we ended off with on Thursday. The equations that describe what's going on here. Two equations, both of them solving for lambda. Lambda stands for what, by the way? Lambda stands for what? The wavelength. Yeah, the wavelength of the light. And it's the same in both equations. The wavelength of the light, and it's typically going to be measured in meters. Let's go with D. That's the one that I find the next easiest one to deal with. D. D is this distance right here. The distance from one opening to another, from the middle of one opening to the middle of the other opening. And that's going to be a really, really small number. L is going to stand for this distance right here. The distance from the openings, the barrier or the openings in the barrier to the screen. This is our screen right here, right? So it's the distance from your openings right here to your screen right here. I made that a capital L. In the equation it says lowercase l, whatever. Yeah, I make it a capital L so you don't get it mixed up with a 1. Now, this is where it gets a little bit tricky. We talked about this on Thursday, and I think you understood it, but it's where it gets a little bit tricky. Okay, you can see that they actually have these maxima or these bright spots or these antinodes labeled. N is equal to 0, N is equal to 1, N is equal to 2. We could do the same thing on the other side. 0, 1, 2, and then so on. X can be this distance right here. But X can also be this distance right here. Or X can also be this distance right here. X can be from any maximum or any bright spot or any antinode, whatever you want to call it, or minimum to any other maximum or minimum. In other words, it can be whatever is convenient for us. So, how does Yamika get the same answer as Fraser if Yamika decides to make X, I don't know, from here to here, but Fraser decides to make X from here to here? It's going to give them two completely different answers, right? It will, unless N is consistent with X. If Yamika made this X right here from the first maximum to the second maximum, then she would have to make N 1, right? From first maximum to second maximum, 2 minus 1 is 1. Fraser makes it from this minimum, the first minimum, to the second maximum. Fraser would have to make N 1.5. Why? Well, because we're really at 0.5 there and 2 there. 2 minus 0.5 is 1.5. So if Yamika does this, that's fine, as long as she does this. If Fraser does this, that's fine, as long as he does this. They'll end up getting the same answer if they do that. Yep. N is the difference in maxima or minimum number. The difference in maximum or minimum number. X is a measurement of a distance, but N is a number. The difference between the two numbers of the max and the min. Yep, Christian?
Those are constantly going to be like that. Like, you always, if it's from that max to the min, it's supposed to be 1.
If it's from 1 to 2, it's always going to be 1. If it's from 1 to 4, and it's going to be equal to 3.
Okay.
If you're going to subtract one max or min from the other max or min. So here we're going from the first max to the second max. 2 minus 1 is 1. Here we're going from really it's the first min to the second max, but the first min is like saying 0.5, 0, 0.5, 1. So we're going from, we can think of it as the 0.5 max to the second max. 2 minus 0.5 is 1.5.
So, like, sometimes each line would be like 3, 6, 9, 12.
I'm not sure what you mean there.
Like, so now it's from going from 1.
This is the first order max. This is the second order max. This is first on the other side, second order on the other side, all the time. You're not going to skip from 0 to 3 to 6 to whatever. Always 0, 1, 2. Now, x is from whatever to whatever, and n is subtracting these numbers, whatever relevant numbers you have, but always going up by 1 each time. Okay? Yeah, Fraser? What's the point if you're dividing by the same number? Well, n isn't the same as x. Remember, n is a number. N is 1 or n is 1.5. X is the distance in meters from one position to another. Okay, does that make sense? So n is just subtracting numbers. X is a distance that separates. Yep.
Can we use like you know that table that we had that shows what n is for certain objects?
Yeah.
Can we use this equation with refraction?
No, you couldn't, because there's no constant value that would be applicable there. Okay, that table that you had for the index of refraction, assuming the same color, each material had a unique but specific index of refraction, and that wouldn't be the case here. Okay, it's not dependent upon the material. It's dependent upon where the screen is. It's dependent upon how far they are apart. It's dependent upon the wavelength and so on. So no, you wouldn't have something like that. No. Okay, what about the last one, theta? Theta, look, we've identified n, I guess. Theta is this angle that's always measured from the central max. Could be measured from the central max to the second order max. It could be measured from the second central max to the second order minimum. It doesn't matter. The difference here between x and theta is that x can be measured from whatever to whatever, whereas theta has to be measured from the middle to whatever. Okay, the starting point of x is not defined. Neither is the ending point. The starting point of theta is defined. It's got to be from the middle, but the ending point isn't. You can do it to wherever you want. And again, as long as n is consistent with that, be fine. Here, n would be equal to, what do we got here? 2 and 0, n would be equal to 2. What about this? Well, we're going from 0 to, what's this one? The second order min is you say 1.5? 1.5 minus 0 is 1.5 there. So once again, you can use whatever theta you want. Yumika can use the top one, this top theta right here, as long as she says n is equal to 2. Fraser can use the bottom theta right there, as long as he says n is equal to 1.5, he'll get the same answer. Now the reality is, you're not going to come across a question where you can just say the value of x or theta is whatever you want. You're going to be given values. My point here is that whatever value you're given, it doesn't really matter. Use what's convenient. Like if you're given a value for between the central max and the second max, that's great, use it. If it's between the central max and the second minimum, that's great, use it. It doesn't matter. Okay, as long as you're consistent with your value of n. Now, one final thing before we do an example question here. I've got a big if, and it is a big if. It's capitalized, so it must be a big if. This bottom equation, gentlemen, is not truly correct. This bottom equation, Devlin, is an approximation. What that means is that when we use it, it gives us a number that's really, really, really good. But it's not perfect. But to a couple significant digits, it's probably going to be just fine. That is, if we use it in the right place. If the angle is fairly small, okay, this angle right here is fairly small, then this is a good approximation. If that angle gets bigger, it becomes not as good of an approximation. Here's the rule of thumb. If theta is less than 10 degrees, we're good to go. we can use that equation. It's an approximation, but it's a good approximation if theta is less than 10. If theta is bigger than 10, then it's not a good approximation. Okay, it kind of falls apart and doesn't work as well. So if you got an angle bigger than 10, just don't use it. Don't use that equation. But I'm going to give you a little rule of thumb here, okay? And it's going to be much easier than finding the angle every time. Listen, if you got the angle, oh, the angle is 11 degrees. Darn it, I can't use this equation. If you know what the angle is, then just use this one, right? Like, why would you even bother if you know what the angle is? It's 11 degrees. Who cares that I can't use this one because I know what the angle is? Just use this one. A lot of times what happens is you don't know what the angle is, but yet the rule is you can't use a second equation if the angle is bigger than 10 degrees. So what do? Well, generally the angle is less than 10 degrees. But our rule of thumb check on that, without having to actually calculate it, Peter, is to say, is L greater than 10x? If L, right here, is greater than 10 times the value of x, that's not a perfect approximation of this, but it's close enough that it'll work for us. Every once in a while, it leads us to have to calculate an angle that we really wouldn't have to calculate, but it's worth it, that 1 in 100 times that happens. Because the other 99 times it saves us enough work that it makes it worth it that one time where we have to do a little bit more work. We'll see a couple examples of this as we go, okay? When we can use that, when we can't use that, and how we deal with it. All right, let's do an example here first. I'll come back to that page in a minute here. 13.8, page 689 says monochromatic light. What does that mean, monochromatic light? One color, okay? Usually we're talking about red light, but maybe it's green light, whatever. One color of light is incident on two slits separated by 0.30 nanometers. I don't like that. The first bright fringe, so that would be the first maximum, is located at 0.080 degrees from the central bright spot, or the central maximum, central antinode. What's the wavelength of that light? That angle is less than 10 degrees, right? Like significantly less than 10 degrees. That means that both equations are good to go. Which one would you want to use, though? Probably the first one. Like if you're given the angle from the central max, why wouldn't you use the first one? The second one is a good approximation. The first one is perfect. Why wouldn't we use the one that's perfect if we already know the angle? All right, we got a distance between the slits here of 0.30 millimeters, or 0.30 times 10 to the minus 3 meters. We're going to say n is equal to 1, not because this says n is equal to 1, but because it's between the central antinode and the first bright spot. It's like this, right? Draw it out. This is your central antinode right here. Okay, this is your first bright spot. 1 minus 0 is 1. N will be equal to 1. Theta is 0.08. And we're looking for the wavelength here. Let's say lambda is equal to d sine theta over n. Okay, pretty straightforward at this point. D is 0.30 times 10 to the minus 3 times sine theta, sine 0.080. Make sure you're in degree mode here. Over n. The value you get for theta here should virtually always be in the range of 10 to the minus 7 meters, because that's visible light. And all these questions you're going to do are going to be visible light. Okay, let's figure out exactly what this is now. Let's figure it out on just one of those calculators here. Let's say 0.3 times 10 to the minus 3 times sine 0.08, press equals, then we divide it by 1, we get 4.18, 4.19, 4.2, I guess, times 10 to the minus 7 meters, done. 10 to the minus 7, right? If you wanted to figure out what type of EMR that was, use V is equal to F times lambda to get the frequency and then compare it against your known frequencies. No, it doesn't always have to be in meters, but I would suggest you do. You could leave D in millimeters, but if you leave D in millimeters, what's lambda going to be in? Millimeters, right? So it's okay. It is okay to leave it there, but generally the answers would be in meters. So you probably want to go with meters all through, as opposed to converting at the end, because wait till the end to convert, and you're probably just going to forget to do it. Make sense? Yep. Yeah. Okay. Have a look at those 3 questions, please. Take a look at number 3. It says the second nodal line of an interference pattern occurs at 0.095 degrees. Again, our angle is significantly less than 10 degrees, right? Now, in the end, it doesn't really matter because when we have the angle measured from the central antinode, there's no reason why we'd want to use that second equation anyways. But you can see that in all of these questions, clearly theta is significantly less than 10 degrees. If you've got to guess whether you can use that second equation or not, then the answer is probably yes, you can. Okay, most times you can, because most times the angle is less than 10 degrees, as you can see with the questions we've done so far. 2 slits are separated by 0.4 millimeters. What's the wavelength and color of the light producing this pattern here? We're going to say second nodal line. This is our central antinode, first antinode, second antinode, third antinode, fourth antinode, and so on. The second nodal line would be this one right here. This is 0 and this is 1.5. So we're going to say in this question n is 1.5. We're going to say theta is 0.095 degrees, and we're going to say d is 0.40 times 10 to the minus 3. 0.4 millimeters or 0.40 times 10 to the minus 3 meters. Want to find the wavelength there. Probably going to use that first equation, d sine theta over n, since we have the angle already from the central max. 0.40 times 10 to the minus 3. Make sure your calculator's in degree mode when you do this, times sine 0.095 divided by 1.5. Let's do this on let's try the fourth calculator this time. See what that gives me. 0.4 times 10 to the minus 3 times sine 0.095, and that bracket, divided by 1.5. 4.4 times 10 to the minus 7. Now it also says what color. Listen, I wouldn't lose any sleep over that question. What color is it? We can figure out pretty easily that it's visible light. Okay, calculate the frequency, visible light. When you calculate that frequency, it ends up being in the higher range of visible light, close to ultraviolet, which probably means that it's indigo or violet, right? But I'll be honest with you, I couldn't distinguish between indigo and violet. Okay, I would know that it's somewhere blue, indigo, violet. I wouldn't worry about the color. Okay, you know that it's not red because it's not at the lower end, right? Okay, specifically which color is it? Whatever. As long as you know that it's visible light, then that's sufficient. Okay, let's do another one here. Another question for you. So it says a student measuring the wavelength of light emitted by Krypton gas sample directs the light through 2 slits separated by 0.264 millimeters. Circle that. The interference pattern is created on screen 3 meters from the slits. Distance between the second bright fringe and the central antinode is 1.18 centimeters. What is one of the? Don't worry about that right now. Let's just say, what is the wavelength of light emitted by the Krypton gas? There is significance to what I crossed off, but don't worry about it right now. So what do we got here? We've got that D is 0.264 times 10 to the minus 3 meters. We've got that L this time is 3 meters. That's how far the screen is away from the slits. Now, second bright fringe, central antinode, first bright fringe, second bright fringe, third one, central and the second, we're going to say n is equal to 2. And we're going to say x is 1.18 times 10 to the minus 2 meters. If I use that value of x, I just had to be consistent with n. It's lambda. What do you want to do? Probably this one, right? xd over n times L, that second equation. But there was a big if there, wasn't there? Remember that? What was the big if? What was the hard and fast rule for when you're allowed to use this equation? That's the rule of thumb, which we're going to end up using. But what was the hard and fast rule?
If it was over sine 10 degrees.
If theta is less than 10. So if theta is less than 10 degrees, we're allowed to use it. We don't know what the angle is, though. We could calculate it. We could calculate it by saying, look, we know what L is. That's the distance from the screen to the slits. And we know what X is. So we could actually find theta there and see if it's less than 10 degrees. But we got a rule of thumb to save us that bother, usually. What was the rule of thumb, Ollie?
If L is greater than 10 times.
What's the value of L here? 3? What's the value of 10x? 1.18 times 10 to the minus 2 times 10. 1.18 times 10 to the minus 1. Is 3 greater than 1.1 times 10 to the negative 1? Yeah, so we're allowed to use that equation, right? What would have happened? Hey, what would have happened if theta, if it hadn't have been greater, if that rule of thumb hadn't have worked? Yep. Yeah, and then we would have had to go through this to find theta then, right? If we can avoid finding theta using the trigonometry, let's just do it. But if the rule of thumb doesn't work, then we're going to have to find the angle. Yep.
How do you find the angle?
Yep. Yeah. You know what L is. You know what X is. Find theta by using the tan function. It's not that much more work, but I think the rule of thumb is a little bit quicker. Avoids trigonometry at least. Okay, what do we got for X here? We got 1.18 times 10 to the negative 2 times D, which is 0.264 times 10 to the minus 3. N is 2 times 3 is the value of L. Let's say 1.18 times 10 to the minus 2 times 0.264 times 10 to the minus 3 divided by 6. 5.2 times 10 to the minus 7. Now, because your angle is small, if you were to go around and find this angle and use the other equation, it's quite likely that 2 digits you would have gotten the same answer. But let's say you got 5.1 using the other equation. If you're under 10 degrees, the diploma exam people will have both of them keyed correct. Even if it's numeric response, 5.1 and 5.2 would both be keyed correct. That make sense? So if you're under 10 degrees, you don't need to worry about which one you're using. You're allowed to do either one. It would probably make sense to do this one. But if the other one gave you a slightly different number, it would also be marked correct because it's actually a better one, right, than this one is. Just the one that most people wouldn't use. I want to show you one quick little thing here. Adele, what was your question a couple minutes ago when I said wait on it for a sec? How do you know the difference in colors? This one said, what is one of the wavelengths of light emitted by Krypton gas? I want to go back here just for a second, okay? This top diagram is produced if you have monochromatic light, one color of light, green light being shone, gentlemen, through two openings. You get a central bright spot, a first order bright spot, second order, and so on and so on and so on. If you have more than one color, polychromatic light, let's say white light, all the colors of the rainbow, then you get a central maximum and a first order maximum and a second order maximum and so on. Now, each maximum that you get, if you have monochromatic, it's just like this, right? One color of bright spot, and then the absence of light is the dark spot. But if you have polychromatic light, then what you get is, let's say, it really should be white light in the middle there, but we can't draw white on white, right? White light in the middle, and then you would get, for each maximum, a red line, and an orange line, and a green line, and a blue line, and an indigo, and so on. My first order maximum would not be the blue, second green, third red. This is my first order maximum. My second order maximum would be this spectrum. My third order maximum would be this spectrum. So what I'm saying is that your question, like different colors, if you used blue light, then you would get a blue spectrum that had a bright spot there, a bright spot there, and a bright spot there. If you used red light, then you would get a bright spot there, a bright spot there, and a bright spot there. If you used green light, then you would get, having trouble erasing that. There we go. You would get a bright spot there, a bright spot there, and a bright spot there. If you used multiple colors, including white light, then you would get a first order bright spot, which consists of a spectrum, a second order bright spot, which consists of a spectrum, and a third order bright spot, which consists of a spectrum. What's the difference between this spectrum that's produced and the spectrum that's produced by a prism? Prism produces Roy G. Biv. Diffraction grating or double slit produces Viv G. Yor. Right? Instead of Roy G. Biv, it's going red to violet, it's going violet to red. Violet light refracts the most. Red light diffracts the most. See that? So it produces a spectrum, but it's backward. Listen, if you ever get a question where you're dealing with polychromatic light, more than one color, here's what I want you to do. Okay, this looks confusing. I know you got stuff all over the place there. Here's what I want you to do. Pick a color. If you're given data about red light, pretend that the blue and the green don't exist. And then just deal with it the way you've dealt with the questions so far. If you're given information about the blue, then pretend the green and the red don't exist. Does that make sense? Like literally erase the other colors. If you've got more than one color, pick a color for which you have data and go with it. Erase the rest of them. It doesn't make it any harder. It just looks a little harder. That's all. Okay. Take a look at the questions that go with the example we just done on page 691, please. Okay, let's have a look at number 3 here. So the student used a light of wavelength 5.00 times 10 to the minus 7 meters and found that the distance between the third node and the central antinode was 0.1 meters. The screen was located 1.2 meters away from the slits. How far apart are the slits? Hey, Adele asked a question earlier about different colors, right? Okay, and then I showed you what would happen if we had different colors, right? What if this question said we had white light and that produced this crazy interference pattern where we had our central bright spot, which was white, and then we had our first order bright spot, and then we had our second order bright spot over here, and so on and so on and so on. What would we do? Well, we've got information about one color. Pick that color. Doesn't matter if you have 3 colors. Pick the one color you have. Don't treat the question any differently, right? So here's the wavelength. Maybe the student used more wavelengths. We just don't know anything about it. Still going to do this the same way. We know the wavelength of the light is 5.00 times 10 to the minus 7 meters. We know that the distance between the third node and central antinode, okay, central antinode, first, second, third antinode, fourth antinode, okay, between the central antinode and the third node, 1, 2, third node, n is going to be equal to what? N is going to be equal to 2.5. The screen is located 1.2 meters away from the slits. We want to find out how far apart the slits are, D. We want to say lambda is equal to, oh wait, what's x? Oh, x is 1.0 times 10 to the minus 1. We want to use lambda is equal to xd over n times L, right? I think that's the most obvious one that we're going to use here. One try. But we got to try that little criterion, that little condition. It's got to be met here. Is L greater than 10 times x? L is 1.2. 10x is 1. Is 1.2 greater than 1? Yeah, barely. Good enough, though. Barely is good enough. Okay, let's rearrange this to solve for D. Take the n out by multiplying, the x down by dividing. This is what we get. Got lambda, got n, got L, got x. Do the math there. 1.50 times 10 to the minus 5 meters. Good there? Yeah, Ollie?
Can you go to number 2?
Yeah. Yeah. Okay, let's have a look at number 2 then, Ollie. Monochromatic light doesn't really matter if it's monochromatic or not, right? We're given information about one color. It doesn't matter if there's more than one color. Just take the information for the one color we have. 2 slits separated by this distance. The distance between antinodes is x. Now, Ollie, it says between antinodes, I said that should be adjacent antinodes. So n is going to be equal to 1. Whether we're talking about the 3rd and 4th antinode or the 14th and 15th antinode, the difference between those two is going to be equal to 1. L is 1.5. So we're going to say lambda is equal to xd over n times L. Let's check our condition. Is L greater than 10 times x? Is 1.5 greater than 0.31? It is. So this is okay. So let's just do our math then. Oh, is that okay?
Yeah.
Is there a problem with n?
I think it was like they used, well,
Let's do one more and then we're going to call it a day, okay? A diffraction grating has 1,000 lines per centimeter. Wait a second. 1,000 lines per centimeter. What does that mean? You know what? We'll come back to that. Okay, we'll come back to that. When light passes through the grating, here's an interference pattern produced on the screen 4 meters away. First order bright fringe, 19.2 from the central bright fringe. What's the wavelength of color of the light? This looks like one of those questions like we've been doing, except for this thing. Let me tell you what a diffraction grating is. Okay, the questions that we've done have been involving two slits. In fact, the first guy to perform this experiment, his name was Thomas Young. We often call it the Young's double slit experiment because there were two openings, two slits. But if we make it not two slits, this isn't the interference pattern, this is the actual slits or the openings. If we make it not two slits, but say 1,000 slits every centimeter, we get the same pattern. Bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, and so on. We get the same pattern. So how do we deal with it? Well, we've got the value of just about everything we need here. L is 4.00 meters. X is 0.192 meters. N is first bright fringe, central, N is going to be equal to 1. Looking for lambda. We got just about everything that we need except for D. Here's what I want you to understand. When you're given the number of lines per centimeter, that's not D, but it's close. That's 1 over D. So we know 1 over D is 1,000. So what do you think we're going to do to solve this problem? You're probably going to want to say lambda is equal to xd over n times L. And you're probably going to do that check here. Is L greater than 10 times x? 4x is 1.92 when we multiply it by 10. Sure enough, we're allowed to use that equation. What's D? Yeah. Yep, flip it over, right? 1 over 1,000, so 1 times 10 to the minus 3 units. Lines per centimeter becomes centimeters. So we got to change that to meters. 1 times 10 to the minus 5 meters. Does that make sense? Get it in centimeters, then convert it to meters. All right, now it's just like the other ones, right? X is 0.192. D is 1 times 10 to the minus 5 meters. N is 1, and L is 4. Oops. Let's do our thing here. 0.192 times 1 times 10 to the minus 5 divided by 4. 4.8 times 10 to the minus 7. If you've got line, listen, if you've got lines per centimeter, don't try to convert it to lines per meter. Get centimeters, then get meters. Okay, convert D to meters, not 1 over D. Get D first, then convert it to meters, and then do your thing. Don't forget that check though. Okay, 9 times out of 10, that check allows you to use the second equation. If it doesn't, find the angle, go from there. All right, let's have a look at these questions, please, on page 693.